Alright, calculus class today, so just want to talk about sections 1.5. So graph the given functions on the common screen, so how this graph's related. So this one is all about the functions of all the exponential function, whether that's exponential growth or decay. So again, this one is just a refresh from pre-calculus, things I need to know for calculus. Okay, so first thing that you need to understand is the model for the exponential function. So the general transformational form is always given as y equals a times the base to the power of x minus h and then plus k. Again, a would be the scale factor, whether that it's considered a vertical stretch or horizontal stretch. If a is greater than 1, obviously that would be a vertical stretch. If then a it's less than 1 but it's greater than 0, so then that would be considered a horizontal stretch. And then the value of h, that just shows you the horizontal shift. And then k, which is the vertical translation. So what we can do here, we can always find out one of the special feature for the exponential function. It's that the asymptote. So whatever the value of k that is, it's not just considered the vertical translation, but also shows that the vertical asymptote. So the vertical asymptote. So like this one right here, so if we just compare that, so y equals 3 to the power of x. Well, if a is not shown, so that means it's just the invisible 1. So 1 times 3 to the power of x. And the value of h is not shown, that means 0. And the k, again, it's not given here, so that means 0. So that means the horizontal asymptote is 0. So it's the x-axis, which is y equals 0. Another thing that we can do, can always set up the xy table to get some points. So plug in 0, so we do have 3 to the power of 0, which is 1, so the y-intercept. And also we can use 1, 3 to the power of 1, so then that would be 3, so 1, 3. And also we can use negative 1. So plug in negative 1 here, so we do have 1/3. So that's a very small number, so 1/3, somewhere here. And once you come up with those dots, you just need to connect them. And that would be the exponential function. So for the domain of the exponential function, it's always considered negative infinity to infinity, because there's no restriction. And then the range for this, so that means y, it's greater than 0. Okay, you can put it this way. Or you can put it with the interval notation. So y is greater than 0, which is open parentheses, 0 to infinity for the range. And now for the rest of this, I want to show you that on the calculator so you can compare that. So this one, 3 to the power of x, the exponential growth, 10 to the power of x, that's another exponential growth model. And then 1/3 to the power of x, so for 1/3, this one can be written as y equals 3 to the power of negative x. As you can see that the negative here, so that means it's a negative right next to the variable. So that means it's reflected over the y-axis. So anytime they see that there's a negative sign right next to the independent variable, it's always the reflection over the y-axis. And then if you see anything that's considered negative outside the whole function, so that means the reflection over the x-axis. So now let me put it into the TI-84 so you see that the graph, what they look like here. So let's just go to y equal. So let me just clear all this. So once you turn on the calculator, so it's always like that. And then y equal, press that first. So the first one that we put in, 3 to the power. The power sign, it's the little caret right here. Power, x, and then enter. And then go down to y2. So y2, this one, I want to put in 10 to the power of x. Another exponential growth model, because the base is greater than 1, so just like a normal basic exponential function. So that's why it's considered exponential growth. And now the next one, y3, so let's put in 1/3. So before you do that, you want to put in 1 divided by 3 with the parentheses. So parentheses open, close. And then caret to the power of x. And then for the fourth one, you want to put in 1/10 or 1/10 to the power of x. And then in order to find out the entire function here, the graph, so you want to go to zoom and then standard. So once you select zoom standard, so that means it gives you the whole perspective of the graph right here. So that is from -10 to 10 on the x-axis, and then -10 to 10. And as the calculator is loading right now, so you can see that the first one, which is 3 to the power of x. So the rest of the graph should be coming up here in a minute. So this one takes up the time for the loading. I probably pressed the wrong key here because I pressed enter again. Okay, let's hit graph once again. Okay, so it looks like we do have a loading problem. Okay, so the way that you can fix it, sometimes that happens, you can always go to second and then off. Okay, so now the calculator just stopped here, and then it's just like a blank screen. And then once you turn it on, and then go to y equal again, so the function, making sure that everything is fine. And now you want to go to zoom, again, standard. So here we go. So the original one, 3 to the power of x. And then the next one, 10 to the power of x. And as you can see, that 10 to the power of x, well, the rate of the growing rate, it's a whole lot faster compared to the blue one. And then the black curve, so that one is considered 1/3 to the power of x. So that one is exponential decay. And then 1/10 to the power of x. Another exponential decay function. So take a look at that, the shape right here. So once you construct that, it looks like an ice cream glass. Okay, so the one that you guys are using, or like a milk-shaped glass. Okay, so now let's look at that something else here real quick. Okay, so for the next page, well, this one is done already, but let me just start it over again for this slide here. Okay, give me one sec. Let me just erase all this. So here's the one that I'm talking about for the transformation. So anytime that the function is getting a little bit kind of complicated, you always want to find the value of a, h, and k. And also, if that's considered exponential model, you want to find the base as well. So back to the vertex form. So the vertex form, once again, is written as y equals a times quantity base b to the power of the quantity of x minus h, and then plus constant k. And the value for this one is considered -1. Again, the indivisible -1 here. So -1 times the base 2. So base is 2. And then h is not shown, so that means it's always 0. And then k is not given, so that means k is 0. Again, according to what I was mentioning before, so k is the horizontal asymptote. And now the rest of this, so the base is 2. So looks like we do have negative here. So negative, that means it's considered double reflection. So the negative right in front of that, the whole function, is considered the reflection over the x-axis. -1 right in front of that variable, it's a reflection over the y-axis. So in order to take care of the reflection, we want to set up the xy table. And you can choose any number you want. So I started off with 0. It's easy number. So 2 to the power of 0, then that would be considered 1. But don't forget about that -1 right in front of it. So it's -1 times 1, so that would be -1. So 0, -1. And now I want to put in 1 for this one here. So 2 to the power of -1, then that would be 1/2. And there's a negative right in front of it, so it's -1/2. So it's 1, -1/2. So 1, -1/2. So down here. And now let's choose another point somewhere right here in the negative region. So let's say -1. So negative, positive, so 2 to the power of 1, so that would be 2. So 2 times -1, -2. So -1, -2, so it's all the way down here. And once you connect those dots, so what do you guys notice? It's another exponential growth model, and the curve, the tail here, is getting close to the x-axis. And then the domain for this one, it's always all real number. Again, there's no any restricted value for the x column, so that's why it covers everything. And then for the range, so the range for this one is considered from negative infinity all the way to 0, but 0 is not included. Now, let's check it out, the other one here. So this one, it might be a little bit confusing. The constant, we started with the constant first. So we can always swap those terms. So this one, we can always start it with y equals the coefficient, negative 1/2, e to the power of negative x, and then plus 2. And then compare it to the transformational form. So we do have a equals negative 1/2. And then the base is e, which is about 2.7. That's the exponential constant. And that's something we talk about in pre-calc. And then, again, the value of h is not given, so it's 0. The negative sign here, so double negative, so that means it's reflection over the x-axis and the y-axis. And then the value of k, for this one, it's a non-zero constant, so that's 2. So what I started first, I started off with the horizontal asymptote, that y equals 2. Again, k, it's not just the vertical translation, but also it's considered the horizontal asymptote if the function is considered exponential. And what we can do next, we can always set up the xy table to get some positions on the graph, the points. So what we can do, we can start it off with easy numbers, 0. E to the power of 0, then that would be 1. 1 times negative 1/2, that's negative 1/2. Negative 1/2 plus 2, then that would be considered 1.5. So 0, 1.5. So 0, 1.5, it's all the way up here. And then I would like to use negative 1, because negative, that would give me positive. So 1/2 times e, so that means like 2.7 divided by 2. So that's going to be about 1 point something. So let's find out. So with the calculator, if you do have a scientific calculator, you can always use that. Or use that, the graphing calculator right here. So 2.7 divided by 2. So here's the value of e. So you go back to second window. Okay, so go back second window here. Well, actually, you want to quit. So you want to go to second and then quit. So again, so it's the value of e divided by 2. So value of e, so second, natural log. So this one you want to type in the power first. So e to the first power, which is the same as e. And then bring down the cursor, divided by 2. And press enter. So it's about 1.35 or 1.36 if you try to round it. So what we got here is 1.36, but it's negative because we're divided by a negative number. So negative 1.36 plus 2, then that will be considered 0.64. 0.64. Okay, so 0.64, negative 1.64, that's somewhere right here. And again, once you get 2 points, or you can get another position here somewhere, simply just connect them. So that's just another exponential growth model. Again, it's the double reflections, because the parent graph is like this. It's always exponential growth. Once you reflect it over the x-axis, or the line of asymptote here, so you get that, the reflections. And then the other one is reflection over the y-axis. So that's why eventually the graph looks like this. It's an upside down exponential growth model. Okay, so now what about finding the domain? The way to find the domain is always finding the type of functions and then its restriction. We do know that the function here is considered rational. So that means the denominator cannot be 0. So we can set the denominator equals 0 first. So we can find the restricted value or the excluded value. So, and now you want to solve for x. So add e to the power of x on both sides, and then you take the natural log on both sides. So what we got here is 0 equals x. So again, this one will give you the restricted value or the excluded value. So that means the domain for this is from negative infinity to 0, and then union 0 to infinity. Again, 0 is not included because that would be considered the restriction. So now for the next one, so we do know that sine, so pretty much the domain for sine, that means it's always all real number. So for this one here, so that it's considered all real number from negative infinity to infinity. And now what you need to do here, you want to solve for t. So in order to solve for t, so what we can do, we can take the natural log on each side here. So natural log of negative infinity, and then natural log of infinity. So for those people wondering, natural log of negative infinity, well, natural log of negative infinity, well, there's no such thing. Because that natural log functions, the restriction is always consider x is greater than 0. So that means for this part here, there's no solution. So the only thing that we can come up with is the, you can set up the boundary. You can say that 0, it's less than natural log of e to the power of negative t. And now what about natural log of infinity? So natural log of infinity, you can say that it's considered infinity. Okay, so as you can see that x is greater than 0, so no matter what that you go with the x value, so eventually it's considered infinity. And now natural log of e, it's always considered negative t. So 0 is less than negative t, it's less than infinity. And other things that the negative sign, don't forget about the negative sign. So you want to divide everything by negative. We do know that it's a compound inequality. So anytime that you divide it by negative, that means you want to flip the sign over. So eventually, this one turns out to be 0. It's greater than t. It's greater than negative infinity. So what this one is saying that, so t must be greater than negative infinity, but it's less than 0. So for the boundary, so this one is saying that it's negative infinity to 0. And that's the domain. You know, a lot of people thought that you can put in any value for t, but the thing is that if you put in a negative number for that, the natural log, it's considered no solution. So with no solution, the boundary here, so that's the asymptote. So gotta be careful with that, the boundary. Okay, so now let's see. Find exponential functions, or the model, with that c times a to the power of x, with the given point. So we do have the 2 point here. One is the y-intercept, 0, 2, and the other one is just like a random position. So it's 2, 2 over 9. So let's find out the value of either a or c first by using the y-intercept. So what I'm going to be doing, so plugging the number, so the value of y, which is 2. And then c, we don't know what that is. The base a, we don't know what that is. X is what? 0. One thing we do know that a to the power of 0 is 1, so it's 1 times c, which is c. So that means the value of c is 2. Okay, so now, once we find out the value of c, the next thing that you can do, you can find out the value of the base, the value of a. So what I'm going to be doing next, so I want to put in 2, 2 over 9 into that function right there. So 2 over 9, so that equals c, which is what? 2 times the base a to the power of 2. So 2 over 9 divided by 2, then that'll be considered 1 over 9. Because that 2 over 9 times 1/2 multiplied by the reciprocal, so it's 1 over 9. And then for the exponent, square root both sides. So we do have a equals 1/3. So once you rewrite it, so this one is considered f of x. So that equals 2 times 1/3 to the power of x. Again, 2, that's just the factor of the vertical stretch. And then the base is 1/3. Okay, so now let's see what else. Okay, so now the word problem. A bacteria culture starts with 400 bacteria. So anytime you see the word problem, you always want to underline the key number, the key phrase. And then double in size every half hour. Okay, so half hour, which is what? 1/2 or 0.5 hour. So we do know that the unit, it's hour, and then the amount here, it's 400 bacteria. And how many bacteria are there after 3 hours? So we do know that this one is considered an exponential growth model. So in general, the structure is considered y of t equals y0 or y0 times e to the power of rt or kt. So y0, this one is called the initial amount. And then y of t is the final amount after t years. So the final amount. And then e just the exponential constant. And what about that r right here? So r is called the proportion constant. You can say that it's just a regular constant here, or proportion constant. And then t, obviously the time. So now, with the information that we have so far, we can find out the value of r. So we do know that 400 is the initial amount. And then it double in size. So double in size every half hour. So that means after half hour later, 30 minutes later, so the final amount would be 800, because that's being double. And then the rest of this, you just want to plug in the number. Again, r, we don't know what that is, so we'll find out. And then the time, which is what, 0.5. So 0.5 t. 0.5 r, excuse me. And now for the rest of this, we can solve for r first. Again, r is considered the proportion constant. So now let's just solve for r. Divided by 400 both sides, so we do have 2, so that equals e to the power of 0.5 r. And now from here, we want to take the natural log both sides. So we do have natural log of 2, so that equals 0.5 r. Again, natural log of e, that's just 1. So 1 times 0.5 r, that's just 0.5 r. So that means r equals natural log of 2 over 0.5, or divided by 1/2. In other words, that's like 2 times natural log of 2. And also 2 natural log of 2 can be written as natural log of 2 squared, which is natural log of 4. By using the properties of natural log, because that's the power, it's a coefficient, so coefficient we can always put it back here as a power, so it's a natural log of 4. So that means for the general form, it's considered y of t, so that equals 400 times e to the power of natural log of 4 times t. And now let's find out the rest of the element here. So how many bacteria are there after 3 hours? So now in order to find out that amount, you can always plug in the number. Since we do know the equation, we can always put it in back to the calculator. So you want to go to y equal, and make sure that you need to clear off the function here, the one that we put in previously. So again, the initial amount is 400 bacteria. Going to the function here, 400. And then times second base e to the power of natural log of 4. So here we go, natural log of 4. And then times t, which is the variable. Now the thing is that, because the function, we have to use that quite a lot. So you want to put in as a general function. And now the next thing you want to do, you want to go to second table. So what I can do here, I can just plug in the time. I can plug in the random time. So again, this one is asking about the population after 3 hours, or the bacteria after 3 hours. So basically just plug in 3 here. And now for those you, the calculator just putting in nothing here, so that means you want to change the setting. You want to go to second, table set, or second window, and make sure that the independent variable, it got to be in as mode. If that's not in the as mode right here, that means you need to fix that. You need to highlight it. And then dependent variable, it's always considered automatic. And now, once again, go back to second in table, or second graph. You'll see that. So after 3 hours, so it's 25,600. So this one, so 25,600. And now, what about the bacteria after 40 minutes? Again, the time, it's in the unit of hour, so we need to convert that minute to hour. So it's 40 over 60. So that means the time is considered 2 over 3 after you reduce it. So now back to the calculator, and then let's put in 2 over 3. Again, second table or second graph. And then for the x value, you want to put in 2 divided by 3. And now it will give you the new value for y, which is 1007.9. So 1007.9. 7.9. So when T equals 2/3, so the bacteria, it's 1007.9. So now, the last one here. Estimate the time for the population to reach 100,000. So that means the final amount. It's 100,000. And we want to set that equal to 400 times e to the power of natural log of 4 times t. So for those you might be having difficulty with solving a problem like this. So again, this one we just want to isolate the variable. So first thing that you want to do, divide it by 400 both sides. And then you want to reduce. Cross out the zeros, the common pair. And now we left with 1000 divided by 4, which is 250. So that equals e to the power of natural log of 4 times t. And now you might be wondering, how do we get rid of the natural log? You can take the natural log both sides. So take the natural log both sides here. We do have natural log of 250. So that equals natural log of 4 times t. So that means the value of t is considered natural log of 250 divided by natural log of 4. So natural log of 250, that's just a constant. Natural log of 4, that's just another constant. So you want to do that on a calculator here. So going back to the normal window. Okay, so second mode or second quick. So now you want to put in that natural log of 250 divided by natural log of 4. So here's the natural log, ln 250 parentheses divided by natural log of 4 and close parentheses. And here we go. So it's almost 4 years. So it's about 3.982 or 3.983. So the time, so it's going to take up to about 4 years. You try to round it up. Okay, so now let's see what else that we have for the rest of this. Exponential growth model. So this time we want to use the graphing calculator to generate the exponential regression. Okay, so using that the capability to model the US populations since 1900. And you want to use the model to predict the population in the year of 2013 and 2021. Now, as you can see that the year here, so it started with 1900 and then 1930, 1960, 1990. So the increment here, so it's about 30. It's exactly 30. But got to be careful with the last column here. And then all of a sudden this one, it goes all the way to 2020, which is the year right now. Okay? So the way to enter the data, so you want to set up the column. It's called L1 and L2. I'm going to show you what to do with that L1 and L2 in a minute. So now for the Y column or the Y value, so this one is just the second row. So the population in million, 76 million, 123 million, and so on and so forth. So now here's the way that you want to put in the data. The way to enter the data into the calculator. So let me just clear all this. So first thing that you want to do, press stats, because this one is all about stat. Anytime that you see like regression, it's all about the stats. And now you want to go to edit. Well, it's already highlighted in edit. So press 1. So now for the first column here, so the first column is the exact same data that you have from the first row. But instead of entering the exact same number, make sure that the initial value, you always want to start it with the x value as 0. Because that is the initial position. So what we got here for the table, so we do have 1900, so that would be considered 0 for that year. And then the next one, we do have 30. So you just go down here, enter 30, and then 60, 90. So the one thing that I messed up previously, this one here, I need to put in, well, you don't want to put in 220. So from 1990 to 220, so what is it? It's 30 years. So this one, you want to put in 30 years. So 30 years. So you started with 0. So the increment here, so 30. Okay, hang on a second here. Well, from the next one, 1990 to 2020, so that's 30 year. So what I did here, I actually put in 120. Okay, making sure that this one is correct. So the increment. Okay, so we got 0, 30, and then 60, and then 90, and then this one here, which is 120. So everything looks good here. So this one, that's fine. And now for the next column, so I want to put in the population. Again, this one is 120, not 3. Okay, so... And now for the next column, which is the second row here, so we got 76,123,179, 250. And then the next one here, which is 423. Okay, so now everything looks good so far. So now what I need to do now, so I just need to put in stats and then calc. So the next one, you want to go to the right cursor. And once you scroll it down, you'll see that it's the exponential regression, and that's the one we want to use. You'll see that there's so many options: linear regression, quadratic, cubic, quartic. This one is also the linear regression with the other outcome. Natural log regression, exponential regression, that would be 0. So press 0 here, or select 0. And then go all the way down to calculate. And then hit enter. So this one basically that generates the model, so the exponential model. As you can see that, so A is 77.58052883, and then the base is 1.039. Okay, so now let's just rewrite it. So the model we just generate, so is y equals 77. The reason why it's 77 because this one is pretty close to the initial population. So 77, we'll just want to use the whole number. And then times 1 point, well, make sure that you need to put in the decimal for the base, because otherwise it won't show any change. You don't just want to put in 1 for the base, okay? So for the base, you want to put in 1.0139. So 1.0139 to the power of x. Again, this one, there's no any phase shift, there's no any vertical translation. So now using the model, so we just want to put in here y equal, because we want to generate the population up to a certain year. So 77 times 1.0139 quantity to the power of x. And for those you want to see the scatter plot, you can always go to plot 1 and then turn on the window, so you see like bunch of dots right there. But right now, since we do have the model, so we just want to use this model. And now going back to this one, so this one you want to estimate the population in 2013. So from 1900 to 2013. Okay, so you want to find out the year right in between, so that would be considered 113 years. So second table, so plug in 113 years. Again, the initial year is 1900 to, so you want to start it from there, and then 2013. So that's going to be 113 years after that. Press enter. So the population is 366.39. So at 2013, so the population, again 113, that's just a year, the time. And then the population is 366.39 million. And then what about at 2020? So at 2020, so that means the time would be considered 120. So put in 120. Okay, so go back to that table here. So this time you want to put in 120. Press enter. So the population would be 403.56. Okay. So for this one, oh, you know what? Let me just fix that. So for y of 120, so the population is 403.56 million. Which is kind of getting close to this number here. Again, this one, the scatter plot. But the thing is that we want to estimate the population in 2021 for next year. So let's just put in that 121. And for that one, so the population would be 409. It's actually 409.17. Now, for those you might be wondering how come the numbers, it's a little bit less compared to this one. So the model that we just figured out here, it's about the exponential growth model. It doesn't directly hit the same position as what we have originally. So this one, once you generate the model, so let me show you that scatter plot. Okay, so if you go to second stat plot or second y equal, and now you want to turn on this plot 1 off right now, so you want to turn that on. So press 1, and now it's still off. You want to press enter right here. And now there's so many selections. You can see the scatter plot, you can see that the dotted, the line curve, and then the rectangular bar, and also you can see that the whisker plot, all that, and then this one is the curve. So what I would like to choose is that type 1. So once you choose type 1, and then you want to hit graph, and let's see what happened here. So the window might be a little bit different, so it doesn't satisfy the exponential growth model because that's a big number. So what you can do, you can always go to zoom. Again, it's not showing anything here, so you want to go to zoom and then hit 0. So you'll see that the whole picture of the scatter plot and the exponential growth model. So as you can see that here, so it started with the initial population in 1900, and then this went all the way to the top. Another thing you can do is you can change the window. So instead of using negative x value, because the year cannot be negative, so it started off with the initial year 0, and then this one, let's say that it's 130 years later. So that means it reached to the year of 2030. And then for the y min, y max, so we just want to change that a little bit. So let's say this one, y min, I want to start it off with the initial population, which is 76 million. We can start it off with 70. Let's make it perfect number. And then for the max, so this one I want to put in 500. Everything else just remained the same. And now hit graph. You guys see that, the scatter plot, the dot, the open circle? See, that's all connected. But somehow at that position it's kind of a little bit down below the box. Because this one, it's like overestimation for that population. Okay, so that's it. So thank you for watching the video today. So I'll see you guys next time. Take care.